Okay, so this P7 video is for gas laws and looking at the molecular model and kinetic theory, and also how we actually get absolute zero from the gas laws. So, the idea of the molecular model and kinetic theory is that we can think about the properties of the gas by thinking about how the particles the gas is made up from behave, these molecules. The important things to realise are what the molecules can do. So, we can have a molecule bouncing around inside a container, which is the blue box here, and we need to realise that molecules move in straight lines and they collide with the wall of the container they are in. Now, thinking about some stuff from P4, when the molecules collide with the container walls, their momentum changes, which means the walls must be exerting a force on the molecules. And so if you remember our stuff about interaction force pairs, that means the molecules are exerting a force on the walls, and that is the origin of pressure. Technically, pressure is force over area, and so the number of collisions and the strength, if you like, of those collisions is going to determine the pressure. We'll come back to that in a second. The other thing to bear in mind is molecules can hit each other as well. But the two main things to think about when we're doing this is that the pressure will be greater if the molecules collide with the container walls more frequently, and if the molecules collide with the container walls with greater force. And really, pressure is kind of the critical thing for understanding the changes that take place in gases when we change other parameters. You should also remember, for example, that if you increase the temperature of something, then the particles are going to vibrate more in the case of a solid, or move faster in the case of a gas. So that's another important fact to remember. And those two things coupled together can basically explain the gas laws by using this idea of the molecular model, all the gas is made of molecules, and kinetic theory. There's a little bit more detail to this if you dig down into it, but for us, this is as much as we really need to know to be able to explain what's going on. I'll mention a couple of these details as we go through the examples of the sort of experiments that you can do to show that these gas laws do work. So let's take them in turn, and we'll look at Boyles Law first. I'm going to assume you've watched the gas law equation video here, so I'm not going to go over in detail the shape of the graphs and things like that. If you want to look at that, go and look at the other video. But just to remind you that in Boyles Law, pressure and volume of the gas can vary and the temperature of the amount of gas are fixed. And that gives us this equation, and that gives us this relationship. And what we're going to do here is plot the current state of our experiment as a little blue cross on the yellow line. So the blue cross is stuck on that yellow line. It can only move up and down it because we have our fixed amount of gas at fixed temperature. So to actually do this experiment, you really need a gas in a container, and the green line at the top of the container here is like a plunger. It can move up and down in the container, allowing the volume to vary. Okay, and we also have a pressure gauge on here so that we can see what the variations in pressure are. And in order to fix the temperature, we have to actively control it. So this whole thing would be thermostatically controlled. It might be immersed in an ice bath to keep it at 0 degrees centigrade. But we need something that's going to maintain the temperature so that we can ensure that we have got fixed temperature. And to ensure the amount of gas is constant, all we need to do is to make sure it doesn't leak so that gas can't move in or out of it. We've got a volume scale up the side and the pressure gauge on the side. And we can see that currently the green line sitting at 2 meters cubed volume, as is our graph, and the pressure gauge is sitting at 10 kilopascals, as is our graph. And what we're going to do now is we're going to increase the pressure on the outside of the container. The little yellow arrows here show the size, if you like, of the pressure on the container. And if the thing is sat there not changing volume, that must mean that the pressure is equalized from the inside of the container to the outside. And so what we're going to do to show what happens here is gradually increase the pressure on the outside of the container. Okay, so when we do that, okay, we won't be in this balanced situation anymore where the collisions of the molecules inside the container on the bottom surface of that plunger will balance out the force from the collisions of the molecules above, outside the container. If we increase the external pressure, then basically that's going to push the cylinder inwards. But as we do that, because there's now less space for the molecules to occupy, they will start to hit the green inside of that plunger more often, and that will increase the internal pressure. So if we gradually turn this pressure up, all that will happen, right, is the volume will decrease, and as that happens, more and more molecules every second will hit the inside of that container wall, increasing the internal pressure. As soon as we stop increasing the external pressure, the whole thing will basically grind to a halt. The internal pressure will equal the external pressure again, and the plunger will stop moving at our new pressure and volume. So we've increased the pressure by a factor of 4, decreased the volume by a factor of 4. Okay. Again, to explain this properly, just to remind you, what you need to talk about is what the molecules are doing in terms of how often they are hitting the inside of that plunger. When we increase the pressure on the outside, that causes the compression, so the volume decreases. As that happens, the molecules in the gas hit the inside of the plunger more frequently, increasing the pressure. And that will continue to happen until we stop increasing the external pressure and we arrive at our new, if you like, equilibrium situation at a new higher pressure and lower volume. So that's Boyles' law in terms of molecular and kinetic theory. Okay, so now we'll move on to Charles's law. And if you remember, in Charles's law, we have a fixed pressure and amount of gas, but a varying volume and temperature. So this time, really, the external pressure is not going to change. So we have a large yellow arrow here for the external pressure, which is not really going to change. In order to really explain what goes on, the internal pressure here in the gas is going to change a little bit, but only just enough to allow that piston, that cylinder, to compress a little bit again. This time we've changed the pressure gauge for a temperature gauge, otherwise known as a thermometer, because obviously we don't need to measure the pressure because it's basically constant. Now, if you remember, for Charles's law, what we have is that volume divided by temperature is constant, which is a straight line on this graph. And the way to think about this one is that we're going to cool down the gas. So I haven't shown it on here. We've basically got some form of refrigerator attached to this container, which is going to reduce the temperature. Okay, and this time, as that happens, that means that the molecules inside the container will move slower, and therefore they will hit the inside of the piston less frequently and with less force, and that will reduce the pressure very slightly on the inside of the container. As that happens, the larger external pressure will compress the gas, and that will just increase back again the collision frequency, so that the pressure on the inside stays roughly constant. It's just very slightly less than the external pressure. And once again, that will keep happening basically until we stop lowering the temperature, at which point we'll get equilibrium again. So I'll just let the animation run with the written explanation so you can see that. Once again, we start off with our balanced external pressure and internal pressure, and then the internal pressure just drops very slightly, so the arrow gets very slightly smaller. Okay, it's basically still at constant pressure. As the thing continues to compress, because the temperature is dropping, the cylinder moves inwards. Eventually, right, we get to that new equilibrium position again, where the external and internal pressure are completely balanced, but at the same value as they were before. This is the important difference. There's no difference in the starting and end pressures here. We just have to tweak the inside pressure just to get it going, basically. And that's happened at our lower temperature, means we have a lower volume. Okay, now this really is the important experiment to talk about when referring to explaining where the concept of absolute zero came from. And we just have to look at a little bit about why this experiment isn't perfect in the real world. And the reason is that you know that if you decrease the temperature of a gas, eventually it will liquefy, it will turn into a liquid. So we can't actually get this yellow straight line all the way down to absolute zero. What happens in reality, if we erase the bottom part of the graph here, is that at some point, basically the boiling point of the gas, or the boiling point of the liquid when it turns into a gas, the volume will decrease rapidly because the gas will turn back into a liquid. So that's when it liquefies. So we never really get to this straight line going all the way to absolute zero. So when this was done, what people had to do was extrapolate, and that means continue the trend from the straight line portion where we have the gas down to find where absolute zero was. So the basic idea was that they then defined absolute zero as the point where the volume of the gas would have become zero if it had kept compressing as it originally did when we reduce the temperature. Depending on which gas you use, you can get very close to this ideal behaviour. Some gases are more ideal than others. We're not really going to talk about exactly why that is now, but there are differences between the different gases. So some of them, obviously, as you know, will liquefy at a much higher temperature, some of them at a lower temperature. So that's how this experiment was used to actually find what we now define as absolute zero. Okay, so that's Charles's law. There's one more to explain, which is in some way a lot simpler, which is the pressure law. And this is simple because we have a fixed volume now. So there's no plunger in this experiment. It's just a sealed box of a fixed size with a fixed amount of gas inside it. And the things that can vary are the temperature and the pressure. So now we have a temperature gauge, a thermometer, and a pressure gauge attached to this box. And if you remember, the relationship is proportional again, that the pressure divided by the temperature is a constant. So what's going to happen this time with the blue dot is we're going to heat this box starting from a low temperature, starting from 100 degrees Kelvin, 100 Kelvin, sorry, no degrees needed, and a pressure of 10 kilopascals. We're going to apply heat to this, and as we do so, the temperature increases, and this one is relatively simple to explain. The molecules move faster when the temperature increases. That means they collide with the walls of the container more often and with greater force, and that increases the pressure. So the pressure law is by far the simplest to explain because we don't have to worry about explaining exactly how this little sort of piston arrangement moves up and down, which involves slightly more nuanced explanation. So that's the three gas laws, Boyles Law, Charles' Law and pressure law, the experiments that are involved in confirming them, and how Charles' law in particular can be used to find absolute zero.